Welcome to a screencast on an introduction to calorimetry. Suppose we have a container that has some cool or low temperature water in it. And then to that, we add some high temperature or hot metal. Well, what ends up happening is the temperature of the water increases, the temperature of the piece of metal decreases, and this occurs because heat flows from the metal to the water. It flows from the high temperature substance to the low temperature substance. Now, this heat flow will continue until both the metal and the water have reached the same temperature, or they're in thermal equilibrium. Now, in an ideal situation, all of the heat that's given off or released by the metal ends up being absorbed or taken in by the water, and no heat is lost from our metal and water system here. Now, this is an example of a very simple calorimeter, and in calorimetry experiments, we will typically measure temperature changes and then relate those to heats for processes, in this case, just a simple transfer of energy from one substance to another, but in general, we'll relate these temperature changes to heats of chemical reactions. Now, in order to do this, we need to use the relationship between heat and temperature change for a substance, and that relationship is given by the equation Q equals mc delta T, with delta T equals T final minus T initial. And in this equation, the Q is the symbol for heat, and heat always flows from the high temperature substance to the low temperature substance. M is mass. C is what's called specific heat, and it is a measure of how readily a substance will change temperature when heat is added to it, or for that matter taken from it. And the specific heat of a given substance has a different value than the specific heat of another substance. So it's dependent upon the substance what the value of the specific heat is. And then T, of course, is temperature. Here are some values of specific heat for a small selection of substances, 3 metals and 2 liquids at room temperature. In specific heat is measured in units of joules per gram degree Celsius. So J, capital J, is the symbol for the energy unit joule, which is what we will most commonly use, and then it's per mass and per temperature change. Now let's see how this works with an example. We have a 53-gram piece of iron, initially at a higher temperature, added to 75 milliliters of water, initially at a lower temperature. The iron and water reach thermal equilibrium at an in-between temperature that's closer to the temperature of the water than the iron initially, and we're asked to calculate the heat for the iron, the heat for the water, and then compare these values and explain what they mean. So to calculate the heat for the iron, we use Q equals mc delta T for the iron. The mass of the iron is 53.1 grams. The specific heat, C, of the iron is 0.438 joules per gram degree Celsius, and this is a value that we looked up in the table. And then the initial temperature of the iron is 84.7 degrees, and the final is 23.1 degrees Celsius, and we do final minus initial for our temperatures. And this gives us negative 1,433 joules when we do the calculation. And then we note that we have 3 sig fig numbers, so our answer should be to 3 significant figures. So let's write it in scientific notation to make that clear. And so the result for heat for the iron is negative 1.43 times 10 to the minus third joules. Okay, next we calculate the heat for water, and it's the same type of calculation, but we use the values for water. Q water equals mc delta T water, and we note that we're given the volume of water rather than the mass, but if we remember that the density of water is 1.0 grams per milliliter, then 75 milliliters of water is 75 grams, and That gets multiplied by the specific heat of water, which is 4.18 joules per gram degree Celsius. And we'll use this enough that it might be worth just remembering the value. And then final temperature minus initial, 23.1 minus 18.6 degrees Celsius. And that gives us 1,411 joules, and it's a positive value this time. Now, if we note that the temperature difference actually gives us a two significant figure number, then we need to round our answer to two significant figures. And so again, scientific notation to make it clear, 1.4 times 10 to the third joules, positive value. All right, so there are our two results. Negative 1.4 times 10 to the third joules for the Q iron, positive 1.4 times 10 to the third joules for the Q water. And to the number of significant figures we have, these are essentially the same number. And so the heat for the water and the heat for the iron are approximately the same in magnitude or size, and they have opposite signs. And if we have a perfect calorimeter, if we don't have heat escaping, all the heat is transferred from the iron directly to the water with none being lost to the surroundings, then we would expect the values of heat to be the same, but one would be positive and one would be negative. And the negative in the case of heat means energy or heat is given off or released, and the positive in the case of heat means that energy or heat is taken in. So in a perfect calorimeter, we will have equal magnitudes of the two Q values, but opposite signs. And that's it for an introduction to calorimetry.